Let us start. I think it may be a matter of taste, but what I like the most about physics is the fact that physics applies to pretty much everything in this world. And today we will be listening to the subject which I don't think we ever heard, which is related to geophysics and climate on this Earth and how ice melts in the polar caps of our planet. Our speaker, we are lucky to have Alex Robel from Georgia Tech, who is one of the leading experts in this field of melting polar ice. I met him in Santa Barbara, where there was a whole program about polar ice on this planet, and it was surprisingly interesting and beautiful physics in many aspects. So that's why we invited him. And Alex received his initial education in Duke University, which is to the south of New York. And then he decided that he should now explore something more to the north and received his PhD from Harvard. And now he is again to the south in Georgia Tech. I don't know why he moved to Georgia Tech. Nice.
You'll find out soon.
So, Alex, please.
Thank you. Thank you, Shora, for the invite, and thank you for having me. I like to joke, I am a lapsed physicist. That was my kind of early training was in physics and dynamical systems theory, and then I drifted to working on problems in the Earth system. But I hope, as you'll see today, never got too far from my roots working in physics. Yeah, so I'm going to talk about sort of two problems that we've worked on in my group. Although I invite you to peruse my website if you're interested in these kinds of problems. And we've worked on a wide range of problems. Again, with a good upbringing as a physicist, I have never found a problem that I don't think should be simplified and turned into equations and then hopefully solved. But today, ultimately, what we are interested in is this problem, which this is a picture that I found on the internet that's close to home for y'all. This is the FDR Drive in New York, not too far from here, and some flooding from a combination of tidal flooding and rainfall, right? And at the end of the day, the reason why we work on these problems is because decision makers in places like New York have to decide how much money should we invest in raising these roads, right? Or should we invest money at all? Should we put more storm drains in? How high should we expect flooding to get in the future? And that is ultimately a scientific question. But it relates to this sort of set of data points. So if you keep on walking downtown from here and you get to Battery Park, and then you walk a little bit further and you go to the Coast Guard station, which is on the southern tip of Manhattan, you will find a tide gauge that has been there since around 1850. It's one of the oldest tide gauges, continuously, well, semi-continuously running tide gauges in the US, not quite the oldest. Boston has the oldest that's been there for 200 years. If you go to Northern Europe, you can find tide gauges that have been there for 300 years. But here in Manhattan, there have been fairly continuous observations of the mean monthly water level at the Battery tide gauge. And what you can see, looking pretty much straight at this plot, you can draw the regression with your eyes, is that sea level has increased by about 0.5 meter over the last century plus. Yeah.
On the 300-year-old one, is it flat at some point?
Yes. So actually, you can kind of start to see it here, depending on where you are globally. The uptick that we've seen in sea level rise began probably somewhere in the late 19th century.
Okay.
But something that I won't talk about today, but is also interesting, is that the ocean is not a bathtub. Sea level does not go up by the same everywhere, and so this 0.5 meter of sea level rise here in New York over the last 150 or so years looks more like 75 centimeters if you go to places in the coastal southeastern US. And if you go to other places like in Alaska or in far northern Maine, sea level is actually falling. And that's due to some complicated reasons with how the land surface moves up and down that I'm not going to get into, but I'm happy to talk about that afterwards. So this is ultimately what we're interested in. And in particular, what we're interested in is where this is going, right? Because we need to make plans for what is going to happen in the future, where, how should we be spending our money to upgrade infrastructure to deal with this issue. Where is the sea level rise coming from? And it's coming from a few different sources, but the one that I'm going to really focus on today is about the melting of our ice sheets. So here we are. Here's a map of Antarctica to give you a sense of scale. If you don't look at these maps, the extent of Antarctica, the horizontal extent of Antarctica is about the same as the horizontal extent of the United States. These ice shelves are the floating parts of Antarctica. This is about the size of Texas. And so we're talking about quite a bit of ice, right? If we took all the ice on Antarctica and we melted it, we would add somewhere in the vicinity of 70 meters to global mean sea level. Now, nobody is saying that we expect all of the ice in Antarctica to melt anytime soon, at least not on timescales of less than thousands of years, right? But here's a nice animation that NASA made. So the data here is from a pair of satellites called GRACE. And GRACE is a pair of satellites that follow the same orbit around the Earth, continuously traversing, basically a complete coverage of the Earth's surface. And the two satellites following the orbit, they precisely measure the range in between the two satellites. So if there is a local change in the gravitational field because there's mass on one part of the Earth, right, because the Earth is not a perfect sphere, then the satellites will get a little closer or further apart, and they'll be able to measure that, right? So these satellites, these GRACE satellites, have been orbiting the Earth. Actually, there's been more than one GRACE mission, but some GRACE satellite has been orbiting the Earth for the better part of the last 2 decades. And so as a result, not only can they measure these spatial perturbations, they can measure how they change in time. And when they do that, what they find is that there has been mass loss, pervasive mass loss in this western part of Antarctica. There has actually been some light mass gain in other parts of Antarctica. But this mass loss reflects ice that is melting from the ice sheet, going into the ocean, raising sea level, and making flooding more common in places like New York.
But you said that in other places, sea level actually goes down.
Correct. But that's primarily because the land surface, right? So the way that we experience sea level
So
as
the
people,
integral is
it's the relative difference between the land surface
I see.
and the local sea level, right? So the sea surface height, right, which is just the vertical position of the ocean, is for the most part going up on average everywhere. Okay, so yeah.
In your plot, it seemed like the sea surface level had been increasing since about 1900.
Mhm.
But at least at the battery. But presumably this melting in Antarctica has only been happening since what, the 60s or so, the 70s.
Yes. So, and that's what I mentioned is that melting of Antarctica is only one part of what's causing sea level rise. Melting of ice in the mountain glaciers, so places like Alaska, the Pacific Northwest, European Alps, that has been occurring since the late 19th century. So that also contributes to sea level rise. Even though there's much less ice locked up in mountain glaciers, they respond much more quickly to changes in atmospheric temperature, for example. And so they have been receding and melting and contributing to sea level rise since the late 19th century. And then at a more basic level, if you warm up the ocean, you warm up seawater, it occupies more volume. And so that is another cause of sea level rise. So up until, if we're talking just about the 20th century, about a third of sea level rise is coming from that thermal expansion of seawaters. A third is coming from the melting of mountain glaciers, and about a third is coming from the melting of the combination of both Greenland and Antarctica. Since 2000, the contribution of Greenland and Antarctica has accelerated, right? And so I won't make a claim. I told you to draw a regression with your eyes before, but if you squint and you look at this plot, right, you can start to see an uptick. There's pretty good evidence from both satellite and tide gauges on the ground that the rate of sea level rise has accelerated in the last 30 years. And that is because this increasing contribution from Greenland and Antarctica. Yeah.
What comprises the very short-term variations? I mean, it is a mean sea level, right? It's not tidal.
This is monthly.
Right.
So the variations are going to come from a variety of things, but you can sort of think of it as sort of month-to-month weather, essentially. You know, if you know, the ocean current deflects that's off the coast, you know, a bit, that will raise or lower sea level somewhat here on the coast. So there are other things that are going on top of this. And if you're interested in planning, those things are important, but obviously there's also just the long-term rise in the average. Okay. So where are we going in the future? This is a figure from one of the more recent IPCC reports that sort of reflects something like a community consensus of where sea level rise. So again, this is a global average predicted sea level rise, where it is going over the next few centuries. And you know, the main thing that I wanted, I could spend a whole talk talking about this plot. But you know, the main thing here is that as you go out further in time, the amount of uncertainty, so the shading here is the uncertainty, the error bars on our projections, the amount of uncertainty increases, right? And so if you're planning for the future, right, this uncertainty makes our lives challenging, makes the lives of planners challenging. And this uncertainty comes from the fact that there are aspects of how ice sheets work and how they respond to climate change that we still don't understand well, or have good ways of including in these computational models that we are using in order to make these projections. Another aspect of this, which I'm about to talk about, is that the ocean and atmospheric system is a chaotic system. And so ice sheets are increasingly melting as the atmosphere warms, but atmospheric temperatures fluctuate on, you know, weekly, monthly, annual timescales. And so there is some intrinsic uncertainty associated with those chaotic fluctuations in the temperatures that ice sheets are experiencing. And so the first part of my talk is going to be focused on thinking about that. All right, so I'm in the physics department, so I have to talk about the 2021 Nobel Prize in Physics, which was cause for great celebration among climate physicists, because it was the first time that climate science had been sort of recognized within the scientific Nobels. So this trio won the Nobel Prize in 2021. And in particular, I want to focus on Klaus Hasselmann. Suge Manabe developed one of the first computational climate models. And Hasselmann also worked on that problem. But in particular, what he's best known for is a stochastic theory for climate modeling, right? There are slow responding aspects of the climate system, of which ice sheets are one, and there are other aspects of the climate system that are rapidly varying, right? So when you have a separation of timescales like this, you might separate two components of the system and then treat one as a stochastic component. And so he develops the sort of some of the basic theory for how this should work. And if you look at that paper, he says, ice sheets would be a great candidate for something in the system to model that have a slow response timescale, right? A slow integration timescale compared to other components of the system. So he said that in a 1976 paper, and then nobody did it for 40 or so years, which is when I first saw the paper and I thought, we have lots of tools in statistical mechanics and statistical physics to tackle some of these problems of understanding uncertainty and how it changes in our ice sheet model projections. Why not use some of these ideas in order to tackle some of these problems? And so that'll be the topic of my first part of my talk, which is stochastic climate variability and the probability distribution of future sea level rise. Okay, so if you've seen anything about ice sheets in the news media, it's going to be a lot of this very overwrought rhetoric about the Doomsday Glacier or melting becoming irreversible on ice sheets. And I'm just going to give you a quick crash course in what that means to a physicist, right? Where that idea comes from. Okay, so here is our very simple side view of what a glacier looks like, right? So the brown line here is the solid Earth, right? The land surface. Glaciers form when snow falls in one place for a long period of time and then compresses over time and turns into ice. So you have this grounded glacier. If it's on a slope or its surface itself is sloped, then the ice is going to want to viscously deform and flow downhill, right? It is, you can think of it as, not you can think of it, it is basically a thin gravity-driven film on a hard surface, and can be modeled in that way. If the ice is extensive enough that it reaches the ocean, then at a certain point, the ice will start to float on the ocean, and you get something called an ice shelf. So this point where the ice goes from being in contact with the solid earth underneath it to being floating on the ocean, where I've put this dashed line, is called the grounding line. It's basically the contact point for this plate, right, that is in contact with something and then floating at another place. So this is the grounding line. Ice is flowing from left to right in this cartoon. And I put here a reverse, what we call a reverse slope, is basically just a part of the bed where the bed gets deeper as you go towards the interior or you go upstream with the flow. And why is this important? Why do we care about that? Let me just show this, right? So this is what Antarctica would look like. We saw a bigger map of Antarctica before with ice on top of it. This is what Antarctica would look like if you took all the ice off of it. Okay, so the brown areas are above sea level. The blue areas are below sea level. So Antarctica actually wouldn't be a continent if you took all the ice off of it. It would be an archipelago. But importantly, so the light blue is shallow submarine parts of the seafloor, and the dark blue are deep parts of the seafloor. Importantly, because ice flows from here to here and here to here, right? You have this situation where the bed gets deeper as you go towards the interior of the ice sheet. So going back to my picture over here, this is why I've drawn this reverse slope. Again, this is a cartoon. It's meant for illustrative purposes. But it is very commonly the case, particularly in Antarctica and many places in Greenland as well, that the bed will get deeper towards the interior of the ice.
Is there water under the ice in any of those places?
Here where it's not floating, yes, you might have freshwater or sort of subglacial hydrological network as well, but not nearly at the same thickness as you might have the ocean. So you would have a thin film or sort of a porous sheet of a scale of millimeters to centimeters in thickness.
But in sort of the darkest blue parts of that map you showed of Antarctica?
Oh, I mean, in those parts, I mean, where there is ice now, there is, yes, a very thin layer, and that's because even though the atmosphere is very cold, you've got 2 kilometers thick of ice there. You've got geothermal heating coming from the earth, and so the ice that's actually in contact with the solid earth there at the bottom is at the pressure melting point. So it will melt and it will produce this subglacial hydrology. I'm not going to talk about that at all, but another very interesting area of research. Okay. So in this simple cartoon, we have ice flow from left to right. And so we can write down a very simple mass balance for this problem, where ice is coming into the system by accumulation from snow coming from the atmosphere, and ice is leaving the system by just ice flow through the grounding. We consider it to be having left the system when it crosses the grounding line, because once it is floating in the ocean, it is contributing to global sea level, right? Because it has to be compensated through buoyancy in the ocean. So basically what we're doing here is we're drawing a box model, right? And I'm gonna write down that box model. Okay. So in this box model, there's only 2 terms, right? There's 2 flux terms. One, again, is the snow accumulation. The other is the grounding line flux. And in this cartoon flux graph, what we are looking at is different possible positions of where the grounding line could be, right? So the blue line is how much ice is coming into the system through accumulation of snowfall, right? And as the ice sheet gets bigger, so we're assuming snow, the rate of snow accumulation is the same everywhere, again, in this very simple world, right? So this blue line is just as the ice sheet gets larger, it captures a larger area of snowfall accumulation, right? And the flux in gets linearly higher. The red line is the rate of ice flow through the grounding line. And I am not going to get into the details of this, although there is very nice asymptotic theory, boundary layer theory, that describes how fast ice flows through the grounding line. But to a good approximation, we can generally say that the flux of ice through the grounding line is related to a power, beta, which is somewhere between 3 and 6, depending on what assumptions you make, of how deep the bed is, right? So the reason why this looks like a cubic function is because it's just reflecting the depth of this cartoon bed that I've drawn here. Okay, and so, right, where these two lines cross is where you have potential fixed, or where you have fixed points in the system. Now, let's say we decrease the amount of snowfall coming in, right? So that's what that's going to do, is that's going to tilt this blue line down, right? If the rate of snowfall is lower, right, then the mass flux in is lower as well, right? And let's say we started over here, like in this picture, right? This fixed point right here is going to move back a little bit, right? Which means that our grounding line is going to retreat, right? Our glacier is going to get smaller, right? When we decrease the snow flux. If we keep on doing that, we eventually don't have a fixed point here anymore, right? And for those of you who have seen plots like this before, this is what we would refer to as a saddle node bifurcation. Okay, so a saddle node bifurcation is where you have a stable fixed point. That's what we had over here, and we have an unstable fixed point, and they meet, and then we no longer have any fixed point after that point. So what does this mean in the real world? What it means is that where you have these reverse sloping beds, if the grounding line gets to that point, and then you reduce the amount of snowfall going into the system a little bit more, then the grounding line will just retreat all the way back to a new stable fixed point without having to force the system further, right? This is just a classical bifurcation, and this is an irreversible transition to this state of retreat, right? And now if we wanted to grow the glacier back to its original state, we would have to increase the snowfall much higher than we originally had it in order to get back onto this branch of the system over here, right? And so that's the sort of classical hysteresis that you see in a lot of systems with these saddle node bifurcations. Any questions about this?
This will now generate a new dip in the new place
A new dip, like in the bed?
at the bottom. Yeah.
I mean, yeah, there's another part of this that I'm not talking about, right? Which is the fact that over long enough time scales, the bed will depress due to the weight of the ice on top of it. But we're not considering that here.
So this is, if you had said to me what climate change is doing,
Mhm.
I wouldn't have said it's reducing snowfall. I would have said it's like melting ice. What you're saying is it's reducing snowfall.
Yeah, I mean, you can see them sort of as parts of the same thing. This is an average, what we would call surface mass balance, which is basically just, it is the source of mass into the system. And what I would say is what this actually looks like in reality is it's increasing the length of the melt season, right? So in summer, when temperatures are warm, then you have melting generally in these places, and this will increase the length of the melt season. Right now, for the purpose, again, of the simple picture, what I'm doing is I'm just saying, what's the average amount of mass influx over the course of the year, right? And so in this system, that's net snow accumulation. And if we increase the length of the melt season, then that's going to be effectively a decrease in the net annual snow accumulation.
And the difference between like the red line and the melting is the red line is coming like flow out, and the melting is coming off the top. So you're just
Correct. Yeah. I'm going to talk the second half of my talk if I get to it, which I probably won't. But the second half of my talk is all about melt on the surface. Okay. So talked about this. So in all of this picture, we thought about climate changing as just this sort of maybe gradual decrease in snowfall or increase in melting, however you want to look at it, right? But in reality, the climate is highly variable, right, on a year-to-year basis. And that produces uncertainty in the system, and particularly uncertainty in when this bifurcation might occur and how fast the system will evolve once the bifurcation starts to occur, right? And so this chaotic variability hasn't really been explored in the context of sort of quantifying the uncertainty in the system. So here is just two examples of measurements of ocean temperature, which is another source of mass loss for glaciers, near glaciers in Greenland and Antarctica, and it sort of fluctuates on a year-to-year and decade-to-decade timescale. Okay, so back to this simple cartoon. Finally get to write an equation. This is a very simple box model again, right? We've got a differential equation for L, which is the position of the grounding line, right, in X on this plot. And the time derivative of that is simply equal to the mass coming in minus the mass going. All right, very simple model, right? And where this variability of the climate comes in, right? This sort of year-to-year variability comes in is, well, we can represent that as a source of noise in the system, right? So now I have rewritten my simple model as one part that has deterministic dynamics. That's what I had on the last slide. And then a second term, which is a stochastic term with some amplitude sigma, right? And then a random variable. Okay, so now I have a stochastic differential equation. And this is exciting because now I can do exciting things with this. One thing that we can do is something called stochastic perturbation theory. This is some great work that was worked out by Woo Sok Moon and John Wetlau for a little over a decade ago. And it is basically a way for just rewriting complicated nonlinear stochastic differential equations and linearizing them. And how are we linearizing them? We are expanding the stochastic differential equation about the purely deterministic solution in terms of the noise amplitude. So there's a lot more math here. This is a schematic of what's going on with this approach. But the idea is what's in the brackets here on the top line is the linearized expansion of what was previously our deterministic model. That's what I had before. And then I still have my noise term. And then I can expand the solution L of the model about the deterministic solution with terms that are a function of the magnitude of noise, right? And eventually what that gets me to is the Langevin equation, right? So this is just a sort of a mathematical tool for taking our nonlinear deterministic equation, linearizing it about the deterministic solution, right? And then getting our classic linear stochastic differential equation, the Langevin equation. Okay. Once we get to the Langevin equation, this opens up our whole statistical mechanics toolbox, right? Because for this stochastic differential equation, we have a deterministic component, right, or a version, right, which we call the Fokker-Planck equation, which describes the evolution of the probability distribution rather than the evolution of an individual trajectory or individual realization with random noise, right? And so here's our Fokker-Planck equation. And the advantage of this is that this has many known solutions for the leading order moments of the probability distribution that is evolving in the system. Okay. And so what do we learn from this, right? What we learn from this is something about the variance, right? So this is the width of the distribution of possible ice sheet states in this system, right? So I'm showing here a schematic on the right of this cartoon model, and in the top are many realizations of the model, right? So, okay, the y-axis is ice volume, right? Or you could think of that as the grounding line position, but it's a proxy for ice volume. How big the ice sheet is, right? So ice volume goes up on the y-axis, and that means that sea level rise is going in the down direction, right? The smaller the ice volume is, the greater the sea level rises, right? And each one of these black lines is one realization of that very simple model, which is different noise forcing, a different realization of random climate variability, right? And early on in the simulation, before we've undergone any kind of bifurcation or anything like that, right? The probability distribution, so that's this blue probability distribution here, is symmetric and it's narrow, right? And as we go through this bifurcation in the system, the saddle node bifurcation, then the trajectories generally start to retreat on average, those black lines moving down on average, but not only that, they spread out. And they don't spread out symmetrically, right? They spread out with a skewness that is skewed towards worst case scenarios, right? More sea level rise, And this comes directly from analyzing the leading order moments of the Fokker-Planck equation from the previous one, slide, right? Which basically shows that the variance, which you can think of as an proxy for the uncertainty in our projections of sea level rise, grows exponentially with essentially the Lyapunov exponent, for lack of a better word, of this system, right? When the system becomes unstable, right, when we've gone through the bifurcation, right, then this parameter omega becomes positive, right, which means that uncertainty starts to grow exponentially. And not only that, if we look at the next moment, which is the skewness, right, we see that the skewness also grows once we become unstable, right? And the direction that it grows in is fundamentally a result of the nonlinearity implicit in this system. So that beta exponent that I didn't want to talk about before, that quantifies basically how nonlinearly the ice flux through the grounding line changes as a function of how deep the bed is, right? That essentially determines the sign of the skewness. And for all values of beta that we think apply in the real world, this skewness will be in this direction, which means that we will have more of our distribution of uncertainty on the side of worst case scenarios, right? So to put that another way, okay, I'll come back to this in a second. To put that another way, right, we are more likely to have worst case outcomes for sea level rise than we are to have good case outcomes, right? We're less likely to get lucky on the good side and more likely to get lucky on the bad side of the distribution. And when you look at much more complicated models of ice sheet change, and so here are just two examples. These are examples that went into those IPCC projections that I talked about before. Those I just showed error bars, right? Those didn't imply anything about a shape of the distribution. But if you look at pretty much any model simulations that make an effort to quantify uncertainty in these future ice sheet contribution to sea level rise, you see this increasing skewness towards more sea level rise. And ultimately that's coming from the sort of fundamental nonlinearity of the system that I was showing previously.
This
Yeah.
nonlinearity, excuse me, this nonlinearity is what generates this strangely looking curve that gives rise to bifurcation.
It is one of the things that generate that cubic curve before, that was just generated by the fact that the bed gets deeper as you go towards the interior, right? But the nonlinearity enhances the sort of cubicness of that curve, basically. Yeah.
The beta exponent you were
Yeah.
talking about before, is that something people can or try to measure?
Yeah, so the beta, I'm hiding a lot of physics in that. The beta exponent ultimately comes from the fact, so ice is a viscous fluid, as I've mentioned, but it's a shear thinning viscous fluid, right? So as you stress ice more, the viscosity changes in such a way that it makes it easier to flow. And so that exponent there basically comes from the exponent in the constitutive equation, which quantifies basically the nonlinearity of the relationship between stress and strain rate in ice. And that has been widely measured for like 70 years. Okay. So the reason why this matters in practical terms, right? So there's sort of a basic statistical physics reason for this. We did it, it showed it in a simple model and it comes up in complicated models. But the reason why this is not great news is because if we are trying to plan for future sea level rise and we have to plan for this long tail of bad outcomes, we end up having to spend more money to be risk averse, right? So for example, if you are building a nuclear power plant near the ocean, which is where we tend to build them because we need lots of water to cool them, right? You need to build it high enough so that it doesn't get flooded in the future, right? And we really, really don't want that to happen, right? So we're very risk averse for that outcome. And so when we look at the uncertainty in potential future water level, right, we're going to have to build the nuclear power plant in this example extra high because we have to account for this long tail of potential bad outcomes, right? And so ultimately, this ends up being sort of a challenging problem for doing adaptation to sea level rise because of the extra uncertainty that basically comes on this side, right? If there was more uncertainty on the low side, right, that wouldn't really affect adaptation outcomes that much. It would maybe increase the likelihood of doing too much adaptation, potentially wasting money with too much adaptation, but it wouldn't be as much of a problem for basically just how much it increases costs in these adaptation measures. Okay. Yeah.
Is this really the best we can do? I mean, the reason you're having this problem mathematically is because you put the stochastic term in.
Yeah.
And you put the stochastic term in because you don't know how to model climate variability more precisely.
Mhm.
Is there any hope of being able to model it better and not having to do this so that you can make a more tight prediction?
Well, there's two sources. I've really talked about climate variability, but actually, even if we're just talking about what we might call like epistemic uncertainty, which is just a lack of knowledge of all the parameters that are in our model, right? Even without stochastic variations in those, that would have the same structure of uncertainty as well. So that sort of uncertainty of like improving our models, like basic physics in our models, you know, that's possible to bring down over time, and that's basically what our field is engaged in. Like that's, you know, as far as climate variability, there's a fundamental limitation to how well we can predict it over time. And it is similar to the fundamental limitation on, let's say, weather prediction, right? Weather predictions, you know, more than a few weeks out are pretty much no different than random chance. And that's just because the fluid ocean and atmosphere system is chaotic. And so you have a sensitive dependence on initial conditions problem, and you can, you know, make your initial conditions better over time. But ultimately, there's always going to be basically a limitation to how far you can predict those things out. And on these longer, weather and climate variability on long time scales are two different things, but they both basically have the same problem.
So even climate on long time scales, hopefully it's chaotic.
Climate variability.
Variability, yeah.
Yeah, I don't want to give you the impression that like we don't understand that if you put more greenhouse gases into the atmosphere, that like the atmosphere will get warmer. Like that's something that we've known for 150 years. And we've been observing it now, you know, for a very long time, right? That's basically like we understand you put it in physics terms, the mean field physics that influence the average climate over long time scales. But this variability, this year-to-year variability, right? This is just a separate, and it's not that we don't understand it, right? We understand where it comes from. It's just a fundamental limitation of living within a chaotic Earth system. All right. I want to get to the second part of my talk. So you're going to see me skip through some stuff, but that's the less physicsy stuff. Second part of the talk is I want to talk about a particular fun problem that we've been working on for a little while, which is melt on the surface of the ice sheet. Okay, so here is a satellite image from 2002 of Larsen B ice shelf. Right, you can see my little map of Antarctica there in the top right, and this shows that the finger of Antarctica that points towards South America, the Antarctic Peninsula, is where Larsen B was at this point in 2002. I apologize for the graininess of the image. This is actually related to the coarseness of the satellites that we had at that time. But what you can see here, so this is floating ice, right? I talked before that it, you know, a glacier flows from the land surface and then it gets to the ocean, and the ocean is not too warm. The atmosphere is not too warm. The ice will then just float out over the ocean and it'll form this floating extension that we call an ice shelf. And so this is a large ice shelf. To give you a scale sense, this kind of area here is about the size of Rhode Island. So it's a pretty large area. And you can see this speckling here. These are melt lakes that are on the surface. This is austral summer. So this is the middle of the warmest part of the year in Antarctica, being in the southern hemisphere. And so these are melt lakes that were forming on the surface of this ice shelf. So this is January 31st. The next pass of the satellite came on March 5th. And what you can see is that that ice shelf is no longer there, right? Or it's been now broken into thousands and thousands of small icebergs, right? And so the question that came out of this that has been a big focus in our field over the last 2 decades is whether we should expect that such rapid collapse events on timescales of weeks are an expected product of climate change, right? So the Antarctic Peninsula, we have good enough records to know that the Antarctic Peninsula has warmed up by several degrees Celsius over the last century, the atmospheric temperatures, and so we're going to get more surface melt on these ice shelves in the Antarctic Peninsula. Should we expect this to occur in on many other ice shelves as well?
The blue color here are also
The light blue color, yeah, the light blue color is fresh meltwater that's like sitting on the surface of the ocean.
Why it has very different fractal structure.
The
Previous one seems to be like parallel strips.
Well, I mean, this is all broken up now. It's not solid ice anymore.
Oh, I see.
Yeah,
It's
yeah,
not on
So
the-
this is now a dispersed granular material, right? But whereas before you had a solid sheet of ice with, melt ponds on top of it. But that light blue is more that you're seeing all of this fresh water that's sitting on the surface of the ocean here, and that's giving it that light blue color. Okay. So what does a melt pond look like from the side? If we're looking at an ice shelf from the side, you might see this melt pond. And if the melt pond gets deep enough, the water can go into fractures that are underneath the melt pond, and it can cause the fractures to propagate down into the ocean underneath, right? And so you can see that here. The water will enter this propagating this fracture, cause the fracture to propagate, and then eventually it'll drain this melt pond. This drainage of melt ponds is something that is widely observed in Greenland. If you look at satellite images of the Greenland ice sheet, which is generally much warmer than the Antarctic ice sheet, so there's lots of surface melting near the edge of the Greenland ice sheet every summer. And you look at successive satellite images, and you'll see a lake several kilometers wide that a few days later is no longer there. And these things have also been observed from the ground, and this has been something that is known to occur for many decades at this point. But so the way that I chose to approach this problem, right? So the fundamental question we're trying to answer is, should we expect ice shelf collapse to unfold this quickly in general, right? Is this always going to be a really rapid process? Is to use the classical sandpile model to attack this problem, or a variant of the classical sandpile model, right? So for those of you who have not heard of this before, sandpile model is basically a model where we are dripping sand down onto a flat surface. And as the sand builds up into a pile, it'll reach a critical angle of repose, depending on the properties of the grains, but those are details we don't need to get into, right? But it'll reach this critical angle where basically the shape of the pile will be on average maintained over time, because further addition of sand will cause these sand slides that you can see in this video, these sand slides that are moving down the edge of the pile. And this is a really classical model because it exhibits something called self-organized criticality, where basically the size of the avalanches that occur on the side of the pile exhibit power law behavior in terms of their size. Okay, so what does the sandpile tell us about ice shelf collapse? So here is a version of the sandpile model that I worked on with a collaborator on this. So we're going to now imagine the ice shelf as a 2D elastic plate, okay? And we can randomly put sites, lakes on this plate that increase in depth with increment at certain increments, right? So this is in the discrete version of this model, okay? And the rules of this model are that each lake, the ice under each lake has a finite strength, right? So when the lake gets deep enough, it exerts a substantial pressure on the ice beneath it. And if it reaches the threshold that the weight of the water is greater than the strength of the ice underneath it, then the water will drain through, as I showed before, the water will drain through the fracture. And when you drain, so we're slowly loading the surface. This is an elastic plate. You slowly load it over time as you put melt on the surface. But then when you drain it instantaneously, the surface flexurally rebounds. And when the surface flexurally rebounds, it causes a ring of damage around the lake. These are things that have actually been observed. You can see them all around Antarctica. They're called dough lines. You see a ring of fractures that form around lakes that have drained. Okay, and so in this simple model, basically the rule is that if the water depth in a site becomes greater than the local strength of the ice underneath it, then the water all drains, and the other melt pond sites within some radius, which is the flexural radius of that rigid plate or that elastic plate, the strength of ice is reduced by some amount, right? And so, for those of you who are familiar with the classical abelian sandpile, this is a variant on that. It is non-Abelian because the water is not being conserved in this system, right? So it doesn't stay within the system, it immediately disappears from the system. But it has a similar effect that just within some local neighborhood that we can set of the draining melt pond, it will decrease the threshold for fracture at those melt ponds. So it ends up looking somewhat similar to the classical model, right? So here's an example, right? We add water to this pond right here, right? It reaches its threshold, and so then it drains in the next image of the cartoon, and that reduces in these ponds around it, it reduces the capacity of those ponds that they need in order to drain. Right, and so what that then causes in this other lake here, which is now at its capacity, is that now that one will drain, right? And then you'll have an end state like this in this cartoon, right? And so what this can do is it can produce a chain of fractures that occurs across the landscape of lakes in this system. All right, so here's the fun animation that kind of shows this in action. Here I put the lakes on just on a rectangular lattice because it makes the animation easier to see. And what I'm doing here is I'm just randomly adding increments of water at a different site on each iteration. And when they reach the threshold, then the ice within some neighborhood breaks, and then the black, so the blue colors are the depth of water, and then the black are places where the ice is damaged. All the way to 0 in this simulation. Okay. So as we add more and more water over time, I'll just show that again. As we add more and more water randomly on the surface over time, we will progressively damage and break the whole ice shelf, right? And so in this example, you see these events, which we call hydrofracture cascades, but they're what you would call avalanches in a sandpile model. You see these avalanches occurring over some localized area. Right? And to go back to our original question that we started this with, right? The question is, could we produce an avalanche or a hydrofracture cascade in this model that spans the entire system within one iteration of the model, right? Which would be to say, can we have a discontinuous phase transition that damages the whole ice shelf essentially instantaneously or arbitrarily fast? And the answer is mostly no. So here is an example from one simulation where blue is the mean depth of water across the whole lattice. The red dashed line is the mean strength of ice across the whole lattice, right? And you can initially see we start with a perfectly pristine ice shelf, no damage, and water that is all just being, linearly piled up, right? Retained on the surface in these melt ponds. And then at some point, the melt ponds start to fracture more and more, and the mean ice strength goes down, but this occurs over some finite phase transition, with respect to the mean water supply to the system, right? So this is classical continuous phase transition. And what we found is if we try, ultimately there are many parameters that we can choose for this model, right? What is the radius over which damage occurs? How big is the system, right? The full size of the system. How much damage occurs when one melt pond drains. But But what we found essentially is that what ends up being important in this system is the radius over which damage occurs when a hydrofracture event occurs, and what that looks like relative to the density of melt ponds on the surface and the full size of the system, right? So for example, this or maybe a trivial example, but if our radius of fracture was the size of the whole system, right? As soon as we got our first event, we would fracture the entire ice shelf and it would be gone, right? Similarly, if we have infinite pond density, it means for a finite fracture length, we always fracture at least one other pond around it, and then this will continue indefinitely. But what we found is that ultimately what limits the possibility of having this discontinuous phase transition, that is to say, a cascade that spans the whole ice shelf, is the fact that in the real world, what this radius of fracture is meant to represent is the flexural length scale of ice shelves, right? So when you unload them, there is some radius around where you get this damage occurring, right? And that is basically due to the fact that when you have an elastic plate and you load it at a point, right, you get some radius of flexure of the plate downwards. And in ice shelves, in sort of the parameter range that is reasonable for ice shelves, given their thickness and their material properties, this flexural length scale is always going to be much smaller than the size of the ice shelf for the ice shelves that we have on it. So ultimately, the answer was no. This probably, like this really rapid event that we saw is probably a special case, and is probably not generically what we expect. And in fact, there have been many other ice shelves that have since also collapsed in this peninsula region of Antarctica, but they've all done so over a time scale of like years to decades, right? As you slowly add more and more water. I'm happy to talk afterwards about what I think happened at Larsen B ice shelf, that one spectacular case. But we don't think that that is going to be generically the case for all ice shelves. Yeah.
And what is the length scale in reality for these ponds?
Like the size of the ponds or the flexural length scale?
Oh, of the ponds.
The ponds tend to be like hundreds of meters to a few kilometers in width.
Those are biggest ones, but there are of course smaller ones too.
There are smaller ones, but those ones are never going to get deep enough to cause fracture. Yeah.
How common are like big wave storms in this area, and if global warming?
Yeah, so that's what I was going to say. What happened at Larsen B? So it's not the big waves. The working theory is, so some of you might be familiar with atmospheric rivers. If you've ever heard of like the Pineapple Express on the west coast of the United States, these are these like long sinuous storms that bring warm, moist air from the central Pacific and then produce the most extreme rainfall events that you get on the west coast of the United States. Atmospheric rivers also happen in Antarctica, and there's pretty good evidence that an atmospheric river occurred this summer at Larsen B that was basically extending thousands of kilometers to lower latitudes and bringing warm, moist air from lower latitudes. So estimates of melt the rate or the amount of melting that was occurring on this ice shelf in this summer are that it was probably 3 times higher than at any other period in the historical record. So probably basically the answer is you're probably just driving the system really, really hard in that case in this event. Yeah.
And a follow-up question. So one of the things you hear about global warming is that extreme like weather events like these are more and more likely to happen. So is something like that, like a big driving factor, going to happen more rapidly in the future, and then we can expect these collapses to happen more?
It's a possibility.
I mean,
that's with atmospheric rivers are tricky. And I think, as you shift the distribution to warmer temperatures, like just mechanically, you expect what we previously considered an extreme event to become more common. Whether the distribution is also broadening is an active area of research. Okay, I'm just about out of time. The last part, which I'm not going to get to talk about, is basically in this previous model, we're just assuming that there are set sites where water forms these lakes. And in the real world, water forms these beautiful patterns on the surface of ice. So here's a fun video taken from a Korean polar research helicopter about a decade ago. This is an ice shelf in East Antarctica. This is a river that is formed on the surface of the ice sheet, and this is a rift. This is actually not the edge of the ice sheet. This is a rift in the ice shelf, and to give you a sense of scale, this waterfall here is about the height of Niagara Falls. So there's a massive amount of water that's moving over the surface, and it's not just forming all of these discrete, disconnected lakes, but there is a full rich hydrological system that exists here. And I don't have time for this, but what I will say is some work that my grad student Danielle Grau has been doing for her PhD is looking at the size of melt ponds that form on the surface and whether we can predict the size of melt ponds. And this is connected to sort of a fundamental problem in percolation physics of if you have a correlated potential landscape and you start to activate sites on that landscape. So in this case, that would be the rough surface of an ice sheet, and you start to put water on the rough surface of the ice sheet. What are the size of the clusters, percolation clusters, or in this case, melt lakes that would form? And the nice thing that we have with the surface of ice sheets that we have found from satellite measurements of roughness on the surface of ice sheets is that the roughness on the surface of ice sheets is self-similar. And so there are some ideas that we can use, and I'm not going to get into this, but they ultimately come from the sort of classical 2D Ising model. In this case, in the Ising model, you have two states, right? And in our potential landscape, right, you have a continuous landscape of potential states. So it's a little bit different. But ultimately, what you're doing is you're finding, right, the low energy state of the system, and what are the size of clusters that form in the system, right? So in the Ising model, you get these kind of clusters here, which if you squint and think about it and are generous, you could say, oh, these look like melt ponds on the surface of an ice sheet. But you can do this with sort of slightly more sophisticated models. And so my student Danielle did this, right? And we can basically ultimately write down relatively simple equations which describe how the size of melt ponds evolves as you put more water on the surface of ice sheets. Why is this important? As you put melt ponds on the surface of the ice sheet, it makes the ice sheet darker, and so it absorbs more solar radiation. So we want to know, right, what fraction of the surface of the ice sheet is covered in melt ponds, right? And what effect will that have on the absorbed solar radiation that's driving the melt? Then the other part of that is, like I've been talking about, water in these lakes can go into fractures on the surface and cause them to propagate. And when they propagate, this can drive more ice loss, right, by fracturing ice off, causing it to break off into the ocean as an iceberg, right? So if we have more of these propagation, these hydrofracture events on the ice sheets, right, this is going to cause more mass loss. And this is very, very recent work from last week from Danielle's last chapter of her PhD. But basically it shows if you use the ideas, right, if you use the predicted depth of melt ponds that you get from this sort of percolation physics way and looking at the bumpy surface of the ice sheet, what you get is a prediction that the depth of melt ponds could increase the amount of ice loss expected in Antarctica by something like 30 to 100%, right? So you can get a lot more ice being lost from the ice sheet when you take into account the fact that melt organizes itself into lakes, and this can drive hydroeruption. All right, so I'm going to stop there. I think I'm now right on time, and I'm happy to take any more questions.
On the phase transition plot, you had that box for realistic parameters.
Yeah.
What makes higher melt ponds, higher density of those unrealistic?
It actually comes from this last part. The fact that when you're on a bumpy surface, you can't arbitrarily jam melt ponds together, right? So like this is ultimately where the simplicity of a lattice model, where you can just jam as many melt ponds in a small space as possible. But that's not going to be the case in the real world. So in the real world, melt ponds space themselves out because there's a finite number of depressions on the surface, and melt ponds will ultimately only occupy so much space.
Oh, you had a question.
Yes. As the ice sheet over the ocean melts, can you quantify the effect that it will have on the ice on land to how much it will move, how fast it will move?
Yes, so that's kind of, so the ice that's floating on the ocean, the ice shelves. So that, for example, that collapse event that I showed the satellite image of, that collapse event directly did not contribute at all to sea level, like sea level rise, right? Because it was already floating in the ocean, right? So the sea level has already accounted for it when it's floating in the ocean. But yes, that's the reason why we care about it from a sea level standpoint is that when you remove that, the ice behind it or upstream of it will flow faster, right? And so, for example, we have satellite measurements of the speed of ice flow there's like 5 or 6 glaciers that flow into that Larsen B ice shelf that collapsed. And after it collapsed, some of them sped up by a factor of like 3 or 4. So it's significant.
Yeah, yeah.
But you said at the beginning that if all the ice on Antarctica melted, sea levels would rise by, and you said either 70 or 7 meters.
It's like 70.
70 meters.
Yeah. Yeah.
That's pretty bad.
Yeah. But I mean, there's been some amount of ice.
Wet right here.
Yeah, there's been some amount of ice in Antarctica for about 30 million years. And you saw it, put some of the projections up there before, like even the worst case scenario projections for the next 300 years are that you might get 5-6 meters of sea level rise in absolute worst case scenario. Ultimately the response time, even with these events that occur quickly, there's basically there's a reservoir time scale for the ice sheet given the speed that it's flowing, even if you sped it up by some amount. And I don't think any credible scientist thinks that the ice is going to disappear from Antarctica in less than 5-10,000 years. And that's only if we make climate really, really inhospitable for ice sheets.
In which case we will not survive till then.
Yeah, there would be other problems, I think, in that case.
Did that 5-6 meters include this 30 to 100%?
No.
Okay.
Yeah, but that error bar is including everything we're trying to understand.
Yeah.
And so that's why we break off these small problems. We turn them into a physics problem that we think we can understand, and then we use what we gain from that, right, to develop these new ways of representing these processes in these more complicated models. But yeah, no, I mean the goal ultimately with all the work that we do is that we're going to improve the sort of physical fidelity of these really complex models. And then the next time when there's an assessment of the uncertainty range, then it'll include that because now it's included as well.
Just
So how much ice is floating in the North Pole, and can that lead to sea level rise, or doesn't it because it's floating?
Yeah, it doesn't because it's floating. There is a technical, actual different answer, which is that it has a very tiny effect on sea level. And this more has to do with the fact that sea ice, which is what is floating in the Arctic Ocean, is salty. And so it sort of changes the density structure of the ocean in such a way that it can affect sea level. But no, the very zero order answer is no.
questions over there, sure.
I have a stupid question. One of your slides said West Antarctica. Which part of Antarctica is the West?
Yeah, it's all arbitrary, right? I mean, if Antarctic scientists had their way, Antarctica would be the North Pole, right? It would be the top of the world, not the bottom. We put all of our human constructs on these things. The reason why West Antarctica is called West Antarctica is because it's the side that's on the pointed on the Western Hemisphere. Yeah.
Yes.
I have another question about the beta exponent.
Okay. Yeah.
Okay, so, your claim was that we know values of this beta exponent because when you put it on ice, it's going to melt, right? Or
It's going to flow.
flow,
Yeah.
it's going to flow. And then you made a claim that the reason that the plot that you were showing shears to the skews to the right is because of the beta exponent values that we have. Are there other beta exponent values where when you shear ice, it still flows, but this thing will skew to the left, let's say?
Within the range of beta values that we're pretty confident applied here, probably not.
Okay, what? Maybe I can ask you more about this later.
No, I mean, like, it's actually, it's a straightforward mathematical answer, which is that, actually. I don't think I had it on the slide, but, no, I did, okay. So the sign of the direction that the skewness grows in is proportional to this kappa value, right? And the kappa value effectively comes from the second term in the Taylor expansion around the deterministic solution, right? So where that comes from, right? So it's the second derivative. It's the second derivative of this QG, which gives you a beta in the front, beta times beta minus 1, right? And so basically, if beta is greater than 3, and we think it's probably between 3 and 6, or there are no theories where beta is less than 3, I guess. Because beta is generally greater than 3, then that kappa value is always going to be skewed in the direction of outcomes. Yeah. And then just anecdotally, so this is all in a very, very simplified model. But again, when you look in these more complicated models, which include this effect of this nonlinearity and have different kinds of nonlinearities and all of that, they all produce skew on that side. None of them produce skew on the other side.
This makes me to ask you a different question about this theory. You pay much attention to the nature of this nonlinearity, but you skip under the rug the question of the nature of noise. You added by hand additive noise because it's the simplest thing that you could do, but of course you can do a variety of other things, such as including noise inside this what you called deterministic function.
I have a slide just for you.
Oh, okay, good.
So in the real complicated system, right? Okay.
Know that.
Well, I skipped this slide, right? So but something that's interesting. So the slides that I skipped over are that we found this theory interesting enough that we wrote a proposal to take our ice sheet models and to develop stochastic versions of them, right? Where all the processes—
I was not a reviewer of—
No. Where all the processes inside of the model include these stochastic components coming from the sort of intrinsic variability in these processes. And as soon as we turned on the model, right, and started doing simulations, what we found is that the ensemble mean state of the model would start to drift, right? And what this ultimately looked like is spurious drift in statistical mechanics, right? Now, it comes from a different source than traditional spurious drift in statistical mechanics, which is the fact that you have all these nonlinear processes that we're putting noise in. And when you do that, basically you take your normal distribution, your random variable, drawn from a Gaussian distribution, and you put a nonlinearity on it, it is going to produce non-zero mean in the resulting distribution, right? This is like a trivial statistics result, right? But what it does is it produces the situation where, okay, so this is a simulation of the Greenland ice sheet where we put stochasticity in these different processes, right? And it's Gaussian boring stochasticity. But when you do that, right, so the shading is an ensemble of 20 simulations, and the solid line for each of these ensembles is the ensemble mean. What you get is this, pretty drastic drift that shows up in the system. So the answer is yes, there's multiplicative noise, there's a nonlinearity on noisy terms, and it produces interesting results.
But the asymmetry towards bad outcome
still shows up, yeah. Yeah, still shows up.
Okay. All right. So on that note, We better go for a better outcome on the 8th floor where there is some.
Yeah, I can give you a dose of optimism over the reception if you would like it. Thank you all very much.